Okay, so, good afternoon. So let's see. So I want to start again with some administration. First, registration, still a hot topic. So as of yesterday, as far as I know, 22 students from the waiting list got emails from the academic office. 6 of them actually haven't registered yet as of this morning. Who are these 6? Not here. Who got email that they can register? Okay, so again, I think it's kind of getting better. So hopefully more people will be able to register. Again, I want to repeat my plea, which is if you plan not to take the class, do it soon, because especially for undergraduate students, they need to register quickly, and I think some of the international students, they don't really. Someone told them that they have more pressure than they should. But anyhow, try to make your decisions. Homework 0. Hopefully all of you did homework 0, and all of you read carefully the solutions that we have. Any questions on this? Yeah.
So you're not audible at the back.
Oh, thank you. That seems to work. Let's see. Is this better? Better. Okay, thanks. So the question was homework 0. I'm hoping that all of you read the solutions, worked on it, and read the solutions. Any questions? It's easy. So homework 1 will be out today, probably in the evening. And I really want to make sure you hear me saying that you should start working on it as soon as it's out. It's going to take you time, and some of it is going to take you time not because it's so difficult, just because we're trying to teach you something, and some of the terminology might be new to you. The way we ask the question might be new to you. Please read it, think about it, so that next week for the sections you're ready with questions, if you have any. Just to give you an idea of what's there, there are 3 questions. 2 or 2.5 are theoretical questions. You have to write solutions. And 1 is programming using MATLAB. We are giving you MATLAB code. So if you don't know MATLAB, you will learn MATLAB by doing this problem set. You just have to modify the code that we are giving you a little bit. So so MATLAB, knowledge of MATLAB is not going to be an issue. The first problem is basically to come up with a learning algorithm for a problem and argue that it actually learns what you want it to learn. The second is a little bit about linear algebra, similar to what you've seen in homework 0. And the third one is about linear separators. And this is the one that requires a MATLAB. So, but as I said, you have 2 weeks for it. It's not going to take you 2 weeks, but you cannot do it in a day. If you haven't looked at it before and thought about it and did some preparation. So please look at it early. Okay. A lot of you ask me questions about projects. I will talk more about projects once I know who's taking the class and how many people take it with projects. Meanwhile, if you have questions, there is a draft instructions on the web that I used previously, and it's okay, I'm going to update it a little bit, but still, that's what's going to happen. Around the middle of the semester, I'm going to ask you to send me a short proposal. The key thing about the proposal is going to be that it makes sense, it's related to machine learning, and it requires you to read a couple of papers. So this is one of the key goals of this project, that you look at the literature, the relevant literature, see what other people are doing on your problem, and do something related to it, beyond it, and so on. So other than that, it's completely open. It could be a survey on some topic. It could be theoretical. It could be experimental. It could be something that is related to what you're working on, especially if you're not a computer scientist and you're using machine learning. A lot of options. Two comments that are not directly related to the class, but this is the best forum to mention it. A lot of you sent me email telling me that you're interested in research in machine learning. In fact, I was overwhelmed by 20-some messages. I responded to some of you, not to all of you. What I'm going to do is I'm going to have meetings on this on Monday evening or late afternoon. And I'm going to send you a message about it. If you haven't received by, I don't know, mid-Monday a message, then it means that I didn't get your message. So send it again. Another unrelated to the class, issue unrelated to the class, I did mention at the beginning of the semester that I'm looking for people that have very strong research interest in programming languages and in machine learning. I'm still looking. I got a lot of messages on that too. Now, I know that all of you are excellent programmers, so you know a lot about programming languages. I'm actually specifically looking for people that have research interest, that they want to invent a new, maybe special purpose programming language, not just that you like to program or know how to program. And specifically, if you know Scala, let me know, because we're going to do it in Scala, and I'm looking for people that can do it. Okay, done with this general thing. There's no question mark after the questions, because it's a comment about questions. All of you ask me excellent questions at the end of the class, and I'd like you, or at least some of you, to ask the same questions during class, because the questions are interesting, and they're interesting to all of you. For example, someone asked me a question at the end of last time about loss functions. And I'm going to take one interpretation of the question, not necessarily the only interpretation, but the question was, we learned last time, we used gradient descent with respect to a specific loss function that was L2, least mean square. And the question is, or one possible question is this good? Or why did we think it's good? For example, is it going to achieve what we want, which is minimizing the number of mistakes? Right? So we started with a bunch of positive examples, a bunch of negative examples. We learned a linear separator. And the way we learned the linear separator is by minimizing some objective function that was a quadratic loss, this LMS. What I said is that we're going to minimize this loss. Is it good? And the answer, it's not good. Or at least it's not what you want to do. And it's very easy for you to play with it. And in fact, we're going to see examples where you can see clearly that while it minimizes the L2 objective, it's not behaving well with respect to the number of mistakes. And you should expect that this would be the case, because we don't know how to minimize the number of mistakes. We are minimizing something that intuitively, or maybe a little bit more than intuitively, we feel it's related to the number of mistakes. But this is really important, because later on, we're going to look at other loss functions and argue that, for one reason or another, they're better sometimes. Again, they will not necessarily do exactly what we want, but maybe they'll do something that is more closely related to what we want. Anyhow, it's a very interesting issue that we will talk about, and it's a question that I'm sure you have. Please ask. Questions? Yeah.
In a log function, how does it work?
Okay, so when I ran the algorithm, I assume that everything is real numbers. Is this the question? So go back to the slides, and you'll see that basically what we had was a function. X is fixed, Y is fixed, and the variables is W, and we differentiate with respect to W. Okay?
Yes, but like if you have a UTX, right?
Yeah.
You can give me a number between minus and
What do you mean, give me a number?
so UTX is a scalar that is
Okay.
and you're subtracting Y that is O.
Okay, let's go on.
So why are we
Because I don't know how to, you have another loss function in mind that has to do with sign, and I don't know how to deal with it. My loss function now is the dot product of W and X minus Y. And I'm going to minimize sum over all the examples. That's my objective now, and I want to minimize that. How is it related to the sign of the dot product? No idea. Hopefully it's related a little bit. So minimizing it will do something with the sign, which is whether I say that it's positive or negative. But as I said, I don't know how to optimize directly with respect to the prediction, to the classification. So I'm optimizing with respect to something that is at least related to it, right? So intuitively, if the distance between the dot product Wx and Y is small, I'm doing okay. Maybe it's small, but on the other side of the linear separator. So it's not what I want. But still, intuitively, it's related. Okay? So this is exactly the point, right? So we are minimizing something in what we did last time. It's not necessarily, in fact, it's not what we want to minimize. But it's related to what we want to minimize. So my goal with this example was to show you that with some assumptions, we can learn something. We can even argue, I didn't prove, but argue that we converge to something. It still leaves a lot of questions. But at least we had a principled way to start with a bunch of data and end with a function in the hypothesis class we cared about, a linear function, that is doing something. And what it's doing is something sensible. Other questions? Yeah. Okay.
How different is it from the batch one? It's like W and X.
So let's go over it. Again, we're going to talk about this a lot, but let me revisit this point. So this is the gradient descent algorithm, where my objective function here is sum over all the data points. Oh, sorry, this is not the objective. I want to go one step. Yeah, okay, this is good. This is my objective. It's the sum over all data points of the target value minus the output, the dot product. What we showed is that if we differentiate this, we get this as our update rule. And the update rule, again, basically, it's an average over all data points of this simple quantity. We can run it, right? Basically, what that means is that in time t, I have some weight vector, and I'm updating this weight vector by computing some average over all the data points, an average of this quantity. That's algorithm 1. Algorithm 2 is doing something very, very similar, only that it's not averaging over the data point. So the way you want to think about it is at time t, you choose an example from your data set, compute this, and update the weight. In this sense, it's stochastic or online or incremental. I don't touch all the examples every time I update the weight. And in fact, we're going to see at least 3, probably more, different algorithms that are doing this. They're going to change the weights in somewhat different way, but they're going to have the same idea. So they'll have a weight vector. They will choose an example, look at it, use it to update the weight, and keep on going. In this sense, it's stochastic. Okay? The disadvantage is that without working very hard, we cannot say that this converges. The advantage is that it's a much simpler algorithm. Okay? Okay, so let's move on to what I want to talk about today. Okay. So this is what we did last time, right? So we talked about modeling learning. We placed all the points here. We talked about hypothesis spaces, and we decided to restrict our hypothesis to the collection of linear functions that best separates the data under some definition of best, and defining best is going to be important. And so this was the hypothesis class that we had. Now, one important thing to realize is that we, in order to address this, we kind of introduced the technical part of the class and gave an algorithm, in fact, 2 algorithms that we just went over now, gradient descent and stochastic gradient descent. So this leaves a lot of questions. One question has to do with expressivity, really important question that we're going to address today. So we decided that we're going to learn linear functions. Now, it's not clear that the target function is linear, right? So maybe we are starting in a bad situation because there's just no way we can represent the target function, right? So there's no way that if you look at your data, we will get 0 error, any way you define your error, because it's not expressive enough. So that's one issue that we will have to live with and think about later on in the class. So, but for today, the question is, can we learn functions that are more flexible or more expressive so that we can actually get 0 error? Of course, there's another question of what can we say about the quality. This is a question that is going to stay with us for a few more weeks. Quality in terms of sample complexity. How many examples do we need to see so that we can do well in the future? We haven't said anything. We're not going to say anything today. time complexity, and quality and the relations between them. Okay, so I want to talk today about decision trees. Yesterday, or the previous lecture, we decoupled the generation of the feature space from the learning. First of all, we said, here's our feature space. You don't like this feature space. I gave a comment that, again, we're going to revisit. You can change your feature space, right? So we gave this example where if you look just at X, the feature space is not good enough, right? We can't really separate with it. But if we double the number of features from X to X, comma, X squared, then we can suddenly do it. So we really decouple the representation of our examples from the learning. What we're going to do today, we're going to put them together and devise a learning algorithm that actually starts with the raw data and, if needed, generates more complex intermediate representation as we go. This is really the key issue about decision trees. You don't need to know ahead of time how expressive is the function that you're learning. The algorithm will figure it out. That's a very important advantage of decision trees. It really transforms the data. There are a few other advantages of this. And for example, if you think about the badges problem that we talked about last week, and you'll think about again because we use it in some of the problem sets, you will see that maybe it's a natural, linear functions may not be the most natural thing to do. Another important thing about decision trees is, people always ask, okay, so what's the best learning algorithm? Why do we need many learning algorithms? And there is no answer to what's the best learning algorithm. But you could relax the question and ask, if I know nothing about my problem, I don't know the domain well, I don't know, how many features are important, very little understanding, which learning algorithm should I use? Then I think my answer is going to be use decision trees. And in fact, I wouldn't suggest to use decision trees as is. I would suggest to use what is called boosted decision trees, which uses the algorithm that we're going to talk about today as a component and uses it multiple times. And this is going to be a very, very good general purpose learning algorithm for various reasons that hopefully we'll understand in a few weeks. So this is one good reason why we want to learn decision trees. And it's very, very useful in many, many applications. Again, even though today what's hot is not decision trees, there are other things that are hot, still I would argue that in many applications this is the best thing you can do. And the two of you that are using Bing as a search engine, it uses boosted decision tree as the ranking function. And it's pretty good, just that you'll know. Okay, so what is decision tree? So I want to talk about decision trees as a representation, and I want to talk about an algorithm. And at the end, I want to start talking a little bit in the context of decision trees about such issues as overfitting and maybe some other experimental issues that come up in machine learning. Yeah.
Just one question on the last slide.
Okay, good question. I actually wanted to change this bullet. Okay, so here is what I mean. You have some, let's assume there is some target function, right? You don't know it, I don't know it, but someone knows it. And let's assume that this, there exists some feature space in which this function is linearly separable. Right? So let's think about a DNF. DNF with clauses of size 3. So the function is something like A, B, and C, or B, C, and D, or D, E, and F, and so on. That's the function. And maybe there are a few other conjuncts there. So there exists a space of features in which this is linearly separable. Specifically, if I will take as my features all possible conjuncts of size 3, like A and B and C, or C and D and F, in this space, this function is linearly separable. Okay? Now, assume that you have, all you know is to learn linear functions. You really want to work in this feature space, because otherwise your chances of learning a good approximation to this function are quite slim. That's what I mean by the target function is linearly separable. In this space, it's linearly separable. Now, if you work only in the space of A, B, C, D, E, F as features, and you learn a linear function, you will make a lot of mistakes, right? You will not be able to separate the data well. And this is kind of the key difference, or one key difference between learning linear functions and learning decision trees. Decision trees, in principle, will allow you to separate, they're not separating, but to classify the data correctly, even when the function is this DNF-like function, while linear functions in the ABC space will not do it. You will have first to invent new features and then use a linear function. Make sense? We will revisit this point a lot, so hopefully there's some understanding of this. Okay, so before I get to decision trees, I want to talk a little bit about representing data, right? So we talk a lot about representing data. Let's assume that you have a relational database or a table. Okay, here I have a table with n attributes, and I want to know something about the people that are represented as entries in this table. So let's assume that I have various attributes there, owns a car or not. So if I have just one thing, I can represent it as a histogram, right? Either owns a car or not. The number of people that own versus those that do not. If I have two features, you know, maybe gender also, now I can represent all combination, owns and male, owns and female, and so on. So I'm going to have this as my histogram. Now, if I have 16 attributes, and I'm going to look at combinations of 2, then I have 16 choose 2 options here. Or if I have just one D histogram, just 16 numbers. If I care about combinations of 2, I have 16 choose 2 numbers. The histogram becomes larger. If I want to do 3, I have also an attribute of, you know, graduated from Illinois or did not graduate from Illinois. Now I have 16 choose 3, which happens to be, I think, 560. A lot of numbers. And it's not necessarily the case that representing, okay, here is another larger number, if I had 100 attributes, it's not necessarily the case that these numbers are going to help me understand the data in any way, right? Because some of the attributes might be more important than others. Some might be completely unimportant. Nevertheless, if I just look at the table, that's the only thing I can do, right? So we want to be able to figure out how to represent data in a more concise way, and also in a way that gives us some idea of what's important, what attributes of the data are important. That's one goal. Moreover, what I want to do is I want to be able to represent it such that it gives me some predictive power. If you ask me a question about a data point that you haven't seen, but it belongs to the same data collection somehow, I want to be able to say something about it. And again, if I just represent data in a flat way this way, I will not have predictive power. So you can think about decision trees as trying to achieve that. On one hand, they're trying to take the data and represent it in a very concise way, or in a more concise way, something that gives some information about what's important. And by doing that, they're also providing me some predictive power. If I get a new data point, I'll be able to say something about it. And on the way to doing it, we're going to use some ideas from information theory as a way to figure out how to represent the data more compactly. So this is what decision trees are doing it. So it's a hierarchical data structure that represents the data basically by a divide and conquer strategy, right? So you can also think about it if you directly come from the classification perspective as it's a non-parametric classifier. We can also use it as regression rather than just classification. We're actually not going to talk about this. But basically, the idea is that I'm starting with a collection of examples, and I'm going to induce a decision tree that will give me a good representation. So for example, let's assume that my collection of examples is here. I have geometric shapes, and they belong to 3 classes, A, B, and C. So I can represent it this way, or I can represent it in a more concise way, this way. I'm going to say, you know what I have here are 2 attributes, color and shape, and then I have a label, whether it's type A, type B, or type C. In this representation as a decision tree, the nodes are tests. The intermediate nodes here are tests that ask what is the shape? Is it a circle, a square, or a triangle? The leaves are the labels, A, B, and C. And there is a branch for each value of the features. So here is the example. And I have 2 tasks, right? So one task is to learn the decision tree, right? To take the collection of examples that I've shown before and represent it this way. And once I have it this way, I can evaluate the decision tree, right? So given a shape, I can go down the decision tree and determine whether it's type A, B, or C. So specifically here, you can see that this data is represented. So I'm starting by asking about the color. If the color is red, I immediately know that it's type B. If the color is green, I still don't know. I need to ask about shape, whether it's circle or square. And once I ask that, it's enough. I classify the data. And you can see that now, if I give you a new shape, you can classify it. That's decision tree. Now, we can think a little bit about the expressivity of decision trees. So it's a Boolean function, or in the example that I had before, it's a 3-valued function. But as you will see, and I deliberately kind of do it just by examples, there's no difference really between Boolean functions and discrete functions. Everything we can say about one, we can say about the other. And you can think about this as a way to split the space. In fact, this is Boolean function here. So forget the previous sentence that I said. It's still a Boolean function. I wonder why no one kind of jumped up and down and said it is a Boolean function. So I split the space of all geometric shapes that can be characterized using color and shape into positive example and negative examples. The question is, how expressive is it? But now I fixed it. Now I have Boolean functions. So how expressive is it? So when I ask how expressive, imagine a Boolean function. A Boolean function in the domain of color can take 3 values. Shape can take 3 values. Are there functions? There are many functions. How many functions are there? What is the size of my instance space? set of examples? 9, because I have 3 colors and 3 shapes. How many Boolean functions can I write if my instance space is of size 9? 2 to the 9. 512 functions. How many of them can I write with a decision tree? With this decision tree? Yeah. All of them. Why?
Because you can rely on.
I can do whatever I want, right? Should be clear. Think about, if you want, people that come from ECE background, think about each path that leads to a positive example as part of a DNF. So I can choose paths so that all the positive examples are expressed and the rest are going to be negative. Or you can think about it as just a way to split the space into 2 types of nodes, positive and negative. I can do whatever I want. So decision trees can express all Boolean functions. Is this good or bad? Okay, so 1 vote for bad. So there are reasons why it's bad. Why is it bad?
There's nothing with green triangles.
It again?
Green triangle is.
Okay, but that's specific for this function, right? So this function is a very specific function, and it only classifies this set of examples. But in general, the family of decision trees can classify everything. Every function that you want, you can express as a decision tree. So it's actually a very important question because it's an important source of confusion. Here is one function. And in fact, this function is not completely defined even. Maybe this was your concern, right? Because I didn't say what happens with a green triangle here. Something to think about, and let's revisit it in a few slides. But what you should agree is that as a class of functions, all decision trees that have internal tests that are color and shape, where color takes these 3 values and shape takes these 3 values, can represent all 512 trees. Yeah?
What if something has unbounded number of
Okay, so the question is, what if I have an infinite attribute space? Good question. Let's wait a few weeks and we'll give examples for what to do with infinite attribute spaces. Right now, I'm assuming that everything is finite. So I have this real notion of a target function that is well defined. Okay, so good or bad, and the reason you said bad was because it's too expressive. The reason it's good is because it's too expressive. So there is a trade-off here that we'll have to look at it. Anyhow, this was what we talked about before. So what we want to do now is we want to start thinking about how to induce these decision trees. Right? So again, I'm talking mostly about discrete category output, even though real values are possible. I just want to make sure that you know that this is a very well-studied collection of representations. People know how to deal very well with large amounts of data, even in incremental fashion, even though we're not going to talk about it today. The algorithms are not as efficient when they deal with a large number of attributes. But this is also possible. There are methods to deal with noisy data. The reason I mentioned it is because I want you to think a little bit about what one means when we say noisy data. There are several kinds of noise that one can talk about. And I mentioned here two. One is the classification noise. When I say classification noise, what I mean is, here's an example. My data says it's positive, really it's negative. There's another type of noise. Here is the example. It says that the color is green, but really the color is blue. It was a measurement noise. These are two distinct types of noise. You want your algorithms to be able to tolerate it. And we also know how to deal with missing values. And again, missing values can come in different ways. Here is my shape. I forgot to record the color. Or something happened and I couldn't see the color. So I have a missing value here. Or I can have a missing label. Here's an example, but no one gave me the label. So we want algorithms that deal with it, and there are decision trees algorithms, slight modification of what we're going to do today, that deal with it. It's a very well-studied example. Moreover, there are ways to deal with features that are not discrete. There could be continuous. For example, it could be the real numbers, and then we'll have to figure out which tests to put in the nodes. And the easiest way would be to discretize it. Once you discretize it, then we reduce it to the standard case. It's a simple test whether y is less than 5 or greater than 5. How exactly to do it, we're not going to talk about, but I'm going to give some hints later on. The key thing from our perspective now is that it's a good representation. It's a very natural representation, right? You can think about it as kind of a 20-question game. And also evaluating it is very easy. Once I give you an example, running down the tree is very easy. But it's completely clear that if I give you data, there are many decision trees that could represent the data. And this is our problem now. Here's data. I want to induce one decision tree. And the question is which of the many decision trees that will be there. So the example that I'm going to use as a running example is an example of will I play tennis today. And this is the domain that we're going to. So we're going to have several features, 4 features, discrete features with these values here on the right. The labels are going to be Boolean, yes or no. And this is the set of examples that we'll use. Okay, so I have here 14 examples. Outlook, temperature, humidity, wind, and these are the values. So now the question is, how do we learn a tree like this? Here's your data. How would you generate a tree? Yeah.
Find an attribute that classifies.
Find an attribute. It's going to be one of these 4 attributes. And then your suggestion for how to choose the attribute is?
Causes maximum separation of data.
What does it mean, maximum separation?
So based on this.
Yeah, temperatures.
For place and many negatives on one.
Okay, so the suggestion is to choose an attribute that splits the data as uniform as possible?
Yes.
Okay, that's a suggestion, but even without the criterion of how to choose an attribute, algorithmically what we want is to choose an attribute, split the data, right? So if I chose temperature, I have 3 values, hot, medium, cool. So I split the data into 3 groups, and then continue, right? Treat each one of these smaller data collection the same way, and keep on going down, right? So this is going to be our algorithm, right? So recursively, we want to build a decision tree top-down. So conceptually, we solve the problem. It's a very simple algorithm, and indeed, this is kind of what we're going to do. The tree that we will choose to use is going to be to start with Outlook. It could be sunny, overcast, or rain, and then for each one of them, we're going to condition again and keep on going down. So here is the algorithm. Given a set of examples where label is the target attribute, the prediction, in this case, yes, no. Attributes is the set of measured attributes, in this case, 4 attributes that we have. I'm going to create a root node for the tree. If all the examples that are labeled have the same label, I'm done. Otherwise, I'm going to do the interesting part of the algorithm. First of all, I'm going to choose an attribute A that is the best attribute. We got one suggestion for best. This is what we're going to talk about next. How do we want to define best? But let's assume that we do have a definition of best. Then for each possible value of A, we generate a new collection, and we're going to denote this collection here SV. This is going to be the subset of examples in S with attribute equal V. If V is empty, we can do whatever we want. It doesn't matter. What I'm suggesting here is actually to add a leaf node with a common value in S. Otherwise, keep on going down. So why, by the way, did I bother even to write this sentence? Because if SV is empty, I can just do nothing. What do you mean by we need a full tree? Right, so the problem is at evaluation, right? So the reason I need it is because what happens if later on, after I land the tree, comes an example, and it has this value. I need to know what to do with it. I don't want to leave it empty. But that's really just a technical thing, just to make sure we understand what we are doing. OK, so we have an algorithm. Now the question is, how do we define best? And when we think about defining best, we need to think about our goal. In some sense, what we want is we want a small tree. Why do we want a small tree? Exactly for the same reason that you wanted a small, concise explanation of why the badges game, why people in the badges game are positive or negative. Because intuitively we feel that if we find a small tree, it better explains the data, it's going to generalize better. This is called the Occam's razor principle that we're going to, in fact, formulate and prove in a couple of weeks. But I think intuitively you feel that this is the right direction to go. The problem is that we don't know how to do it. Yet again, given a data set, finding the minimal decision tree that represents this data is NP-hard. So instead, what we're going to do is we're going to use these greedy heuristics that is biased in such a way that it will find a small decision tree, but it's not going to find the smallest decision tree in general. So how do we do it? So let's generate some intuition to what we can do. So here is some data. I have here 200 examples, and I basically simplified it. So I have 50 examples that have features A equals 0, B equals 0. It's a negative example. All of them are negative. And then I have 50 examples that are A equals 0, B equals 1, also negative. No example comes with A equals 1 and B equals 0. And 100 example comes with A equals 1 and B equals 1. Which attribute would you choose to split on first? Why? So you choose A because once you look at A, you know the answer, right? This is the tree that you'll get with A. You look at A, and you know what are positive, what are negative. You don't need to ask another question. On the other hand, if you split on B, you don't get purely labeled nodes, right? You ask B, and you know, OK, if it happens to be 0, you know that it's a negative example. But if it happens to be 1, you have to ask another question. You get a larger tree, right? So basically, you chose A because you get purely labeled nodes. What happens if I change the data a little bit, and I'm now adding 3 examples in this category? A equal 1, B equal 0, negative example. I have 3 examples. So this is my data set now. Which attribute will you choose now? Still A. Okay, everyone who thinks otherwise? Everyone agrees that it's A. Now, again, if we think about it in terms of the structure, it's going to be the same structure, right? So if you look at B, as before, if it happens to be 0, I got it. If it happens to be 1, I have to ask another question. Same thing with A. If it happens to be 0, if A is 0, I know that it's a negative example. If it happens to be 1, I have to ask about B. But when I put numbers here, what do you see? Condition first about A, I almost know the answer. It's almost purely labeled nodes. And it's so I'm in a much better situation here than I'm here, where I just know something about a quarter of the data. Right? So this is the intuition we want to develop of how to choose the best node. Yeah?
In a decision tree, do you always just split on as two?
Okay. Excellent. In principle, yes. And in fact, I'll give examples. There is literature that splits on combinations of features. Specifically, people split on linear combinations of features. So 3A plus 5B, greater than something or less than something. And there are packages, in fact, that do this. It's going to make life a lot more complicated. So we are not going to do it. The standard decision tree will not do it because you often don't need it, because the decision tree algorithm itself is powerful enough to identify the combinations that you need. But certainly this is a legitimate and important question. And as I said, people have done it. Yeah. Okay, not specifically A times B, but some combination of your attributes, right? So you could imagine. So in the example that I gave before, think about again continuous numbers because it's easier. Let's assume that your attributes are continuous. So you can think about the decision trees as splitting your space to axis parallel rectangles, right? So you choose x equal 5, to the left of it something, to the right of it something, and then you choose y equals 7. Above it, below it, and so on. So an alternative could be to choose some diagonal lines, which means, 2x plus 3y greater than 5, right? So this would be more expressive in principle. Of course, you will have to figure out how to choose this combination, right? So you add another complication. But in principle, you can imagine that this will be more expressive, right? So, but again, I'm not going to talk about it. So right now, we define the feature space. We're going to work with this feature space. Yes?
Why does it matter that we have 3 or
Okay, so that's the key question. The key question is, even though structurally these two trees look the same, you all have the intuition that you'd like to split on A first. And I want to quantify it and give a measure for how do we want to choose the attributes, the top attribute. And I'm going to continue with this now, and let's see if you have the same question later. Yeah? Of course, good question. I'm cheating a little bit. I just wanted to give you some intuition, and I didn't think about this case. Yeah. Of course, I need a tree to be able to classify all the data, right? If you remember, when I gave the algorithm, I added this line that I I actually don't need this line. I only need it for the test, which is the example that you just given. So this was just to develop some intuition for how do you want to choose attributes. Now, in practice, even though you think that A has the advantage, we need to quantify these things. And what we want to do is we want to do this. We want to come up with a criterion. So there are several criterion that people have developed in the literature. The most popular one is based on information gain, originated, about 30, 40 years ago with the ID3 system of Quinlan, and this is why the name of the algorithm that I'm giving here is called the ID3 algorithm. And the basic concept that we need is the concept of entropy. So what is entropy? Again, I assume that 5 of you have seen entropy before. Most of you probably haven't. Entropy is a property of a probability distribution. So we're going to think about, given an attribute, it takes multiple values. A different number of examples satisfy each one of these values. So we're going to think about it as a probability distribution over the values that this attribute can take. And we're going to quantify this probability distribution somehow using entropy and use this as a measure to figure out whether this is a good attribute or not so good attribute. How are we going to do it? So let's define entropy. So if all I have is binary classification, so I have P plus is the proportion of positive examples, P minus is the proportion of negative examples. In the set S, I'm defining the entropy of S as this measure. So it's the negative of P plus log P plus minus P minus log P minus. Let's take an example. So what happens if all the examples belong to the same category? That is, let's assume that P plus is 1, P minus is 0. If P plus is 1, log P plus, log 1 is 0. So I have 0 here, and I also have 0 here, because it's 0 times log of something. So I get 0. So if all the examples belong to the same category, entropy is 1. If, on the other hand, they are equally split, so I have here log of, I didn't ask you which base I should take this log. What do you think? One suggestion for 2. Why doesn't it matter? It's only a constant factor, right? If I choose base 17 instead of 2, right? So the base of the log doesn't matter. I'm going to use it as if it's 2, because it's easier for us to think this way. But it's important for you to realize that it doesn't matter. So let's take this example of 0.5, 0.5. So what I get here is log base 2 of 0.5 is negative 1. And here negative 1. With these negative halves here, I'm getting 1 as the entropy. Okay? So that's entropy. Now, I can generalize this definition now if I have multi-values, right? So I have a distribution over 9 things. So P1 up to P9 is going to represent the fractions. And it's still going to be the sum over 1 to 9, pi log pi to the negative value. Okay? So that's a very important but relatively simple notion. So let's just try. Here are 3 examples. This is an example where I kind of know that it's positive examples. Right? Most of the examples are positive, so the entropy is low. Right? It's almost the case all pluses. This is the case in the middle where there's more pluses than minuses, but it's about the same. And this is an extreme case where it's uniform, and I really know nothing. If you just sample an example from there, I don't know what's going to happen. So the entropy is the highest possible, right? So entropy really is uncertainty. The level of uncertainty I have if you just choose randomly an example from this domain. Okay? So here is another example. Or let's look at these three examples. So what's going to be the entropy here? Low, high? Who says high? Who says low? More low than high, right? Because I basically know what's happening here, right? This value, 1, 2, 3, 4, the fourth value dominates. I kind of know if you give me a random sample there, what's going to be the label there. It's going to be the fourth label. This is going to be a little bit higher than this. Agreed? Because I have more uncertainty here about what's going to happen. And what's going to be the one in the middle? Okay, so let's first agree, high or low? High. High. What's the value? 1. Why 1? Log of 8, right? Log base 2 of 8, let's say, so it's 3, right? But it's high. Okay, so we understand entropy, and it's an important notion, really. This is what it gives us, right? If you have high entropy, you have a high level of uncertainty. You don't know what's happening. If you have low entropy, you pretty much know what you're going to see. So our goal is going to be low entropy. We want to find attribute such that if we look at the values of these attributes and how many data points belong to each one, it's going to give us low entropy. We are almost at the leaf. We kind of know what the decision is, or almost, right? This is the reason we chose A earlier. So we want to aim at low entropy. So more specifically, this is the definition that we're going to have. So we're going to define something that is called information gain. And the information gain of an attribute is the expected reduction in the entropy caused by partitioning on this attribute. Right? So we're starting with something, the entropy of the overall set. Because we are running a recursive algorithm, every time we're going to start with another set. And then we're going to split, right? So SV is going to be the subset of S for which the attribute has value V. So I'm going to look at the entropy of SV, and I'm going to average it over all possible V's, all possible values that this attribute take. Okay, so this is going to be the expected entropy relative to this attribute. So I'm weighing the entropy of each partition by its size relative to the original set. And as we said, if we have partitions of low entropy, very imbalanced splits, we kind of know what's happening. We are closer to the leaf. We want that. So low entropy means high information gain. Right? That's what we want. We want to maximize the information gain. And now you can go back to A and B from before and see which one is better. And you'll see that your intuition was actually the right intuition. Okay, so again, high entropy versus low entropy. This is what we want to play. So let's start. I see that I have some alignment problem here. We'll fix that. But let's start with the will I play tennis today and run through an example. So this is my data set. So I have, as I said, 14 examples. In order to figure out the entropy of the data set, which is my original S, I'm going to count how many positive and how many negative. 1, 2, 3, 4, 5, 6, 7, 8, 9 positive. So I have split 9, 5. And this is going to be the entropy of the data set, right? 9 out of 14 are positive, 5 are negative. The entropy is this. That's my starting point. Now I need to choose an attribute. So basically, it's a search algorithm. I'm going to try each one of the attributes and compute the information gain for each attribute. Here is, OK, this is just showing you again the data set. And I'm going to start with Outlook. So for Outlook, I I can choose sunny, I can choose overcast, and I can choose rainy. For the sunny case, let's see if we can count. 1, 2, 3, 4, 5 are sunny. 1 positive, positive, missed 1, 2 negatives. It says 3, but I don't see it, but I'm sure you see it, so I believe it. 3 negatives, 2 positives, so that's what we get, right? It's easier with overcast. So let's look at overcast. So I have here a positive example, another positive example, another positive example, and another one. That's easy. I know how to compute the entropy. It's going to give me 0 entropy. I just know that if the value is overcast, it's going to be a negative example. And the rainy, again, I have 5 examples, and 3 are positive, 2 are negative. Must be the same value that I got there because it's the same split. So now I can compute the information gain of overcast, and it's going to be this, right? So again, it's the expectation, which means the average. 514 times this, 414 times 0, 514 times this, that's what I get. And the information gain is where I started minus this. I have a value for overcast. Now I have to do the same for the 3 other things. And I'm going to do it for 1. This is humidity. So again, for humidity, I have normal, high, and that's it. So for high, so again, I have 7 examples. It says 1, 3 of them are negative, and 4 of them are, what's happening? Okay, sorry. That's not what I wanted to say. That I put the number for the next step of humidity here, but let's, so basically I have to do the same thing for outlook, humidity, temperature, and wind, and these are the numbers that we get. I think the numbers that I had before were wrong, but we'll check. Either way, what we get here is that outlook is the right thing to choose. So I'm going to split on outlook, and that's what I get. So the rest of the process is simpler because now I have 3 problems. Each problem has less examples, right? So I have here 5 examples. Here I have 4 examples, but I don't need to do any work. And I have another 5 examples here. And I have to repeat the process in exactly the same way. So every attribute is included in the path until every attribute is included in the path, or I'm done because all the examples in some place have the same label. So this is really the same process. This is what I get if I'm just running here one more step. So if you look in the sunny case, right, so I'm taking these 5 examples. Again, so this is my data set now, right? I have a smaller data set. Instead of 14 examples, now I have 5 examples. And I have to look again for each one of them. If I look at, for example, let's say temperature. So for temperature, I have, for hot, I have negative examples only. So I know that the entropy is 0. For cool, I know that the entropy is 0. And for mild, it splits evenly between negative and positive, so I know that the entropy is 1. So it's easy to compute, right? So I had 0 for the hot and the cool, and I had 1 for the mild. Okay? So it was easy to compute because everything was extreme cases. And I know that it's basically the 0.97 that I started with, which was the entropy of this set, minus 2/5 gives me this. And again, I need to do it for the 3 other attributes, and we're done. So overall, this is what we're going to get. This is going to be the tree. And I don't know if it's the smallest tree that you can get here, but this is the tree that ID3 gave us. Overall, this is the algorithm, right? So we basically recursively go over the data set. We ask whether we're done. If we're not done, we find the best features, add children to this feature, and keep on going. Questions? Okay, so this is really what we've done here, right? So we did a search algorithm. We did a heuristic search because we don't know how to do what we really want, which is to find the smallest tree. Notice that we don't do any backtracking at this point. We just run the algorithm. And in principle, we make statistically based decisions using all the data, right? So you gave us all the data, and we use that. Now, there is a little bit of a caveat with this fourth bullet here. What is it? Is it true that I'm making decisions using all data? Yeah, but all data that we have. So I had 14 examples, and I'm making statistical decisions based on these 14 examples. Right, so it's true for the beginning, but as I go down the tree, in fact, I'm making decisions based on smaller and smaller pieces of data. And you could expect that my decisions are less statistically robust as I go down the tree because I'm making them based on smaller data sets. And this is actually an important thing because maybe at some point you could say, you know what, I don't have a lot of examples now. Maybe I'm not going to work too hard and compute entropy, just go by majority here. Or not even include more elements in the tree once the data set I'm deciding based is becoming too small. And this is going to be very, very important to the next slide about overfitting. I'm going to go back to the history a little bit next time. So this is a very important issue in decision trees, and in fact, not only in decision trees. The idea is that as I train the data and I grow the decision tree, I always increase the accuracy. Right? Because I fit the data better and better. But this does not mean that if you give me some data that is set aside, I'm also improving the accuracy on it. Because as I grow the tree, I overfit my training data. I'm not sure what's happening to the test data. And this is an important principle that we will have to think about how to recover from. So you can think about now how to recover from something like this in the context of decision trees. Question number one. You'll take it home and think a little bit about it. And in fact, you can also think about what happens if you don't learn a decision tree, but rather you learn a linear separator, just like what we did last time. What would be a good way to avoid overfitting there? Not the same thing, but the same conceptual question, right? So I have training data. You know a natural way to overfit the training data here in the case of decision trees. Just grow it all the way. And you want to think about a way to avoid it, but also think about how to avoid it in the case of linear separators that we did last time. It's going to be an important question that we'll deal with throughout the class. Okay, thank you. Have a nice weekend. And look at the problem set that will be released tonight.
I sent this email to you about registration, but I didn't get your email, so I still couldn't.
So, yeah, as I...
Just